Good morning or good afternoon, everyone. So our next talk is by Dr. Kifayatullah Lon. He's an assistant professor at Chandigarh University. His research focuses on fractal geometry, fixed point theory, and iterated function systems. His broader research interests include exploring the intersection of analysis, dynamical system, and emerging application in machine learning also. Today, he will speak on generation of attractors by weak 5 tupling iterated function system. Thank you, Dr. Gifayat, for accepting our invitation. And over to you, please.
Yeah, thank you very much. Good morning, everyone present here. So, thank you very much for giving me this opportunity to present my research here. So, this is the work that I'm doing with my one of the colleague in the NIT Jalandhar. So, here I'm just going to show how the different fixed points are generating the iterating function system. The question is I will just pose the question again during this presentation. So the main thing is that when we are defining the iterating function system, is it always possible to find the iterating function system with respect to the every contraction? So the outline of my talk will be about the introduction. First, what are the fractals, why we are using the iterating function system, then the literature survey, what are the developments had been done in this way, then what are the preliminaries in the cyclic weak function, then the results that we got from this cyclic weak by tupling IFS. So let's go to the introduction. As you know that the Euclidean geometry is not enough to just modeling the natural objects. So then there are the limitations that we are usually finding in the integer dimensions. So then the Mandelbrot came in 1975, who introduced the concept of fractal, and he used it to say that the Euclidean geometry is not enough to model the natural objects which are very irregular, which have the very complex structures. So like these are some of the shapes that we have in the nature, and these are very irregular, even beautiful but very irregular. So here is a very important quote of the Mandelbrot, that clouds are not sphere, mountains are not cones, coastlines are not circles, bark is not smooth, does nor does the lightning travel straight line. So if we will see the lightning and all other natural objects, everyone is very complex. Even we can just approximate these, but with the Euclidean geometry, but that's not enough. So that will be the approximation, but not that much correct, or that much uh, that has the error. That's more than what we will just approximate it by the fractals. So then still the fractal has not any particular definition yet, but on the characterization of the set, the Kenneth Falconer has mentioned some of the characterization definitions in his book, that he said that if we have a set that has a fine structure, is also we call it as a fractal, or a set that is too irregular to describe in traditional geometry language, whether it is irregular locally at a point or globally, we say it is a fractal. Or by the characterization of the self similarity, he said if a set has some form of the self similarity, again it is a fractal by that characterization. And this is one of the main thing and the important thing, that we are mathematically using it, that when we have the fractal dimension greater than its topological dimension, we call it as a fractal. And in most cases of the set, so we see that is very simple way. That means when we have the recursively means the same set we are getting when we will zoom it again and again. So that means that's a set is defined in a very simple way and recursively, so then we say it is a fractal. So then some of the fractals that we are usually generating by the mathematics is called the deterministic fractal. That means we are using the functions to define them. So the fractal is defined as an object that appears self-similar under varying magnification degrees, and we call that the deterministic fractals. So that is the definition. So then this self-similarity properties has been used by the Hutchinson, and he defined the iterative function system. Then it has been popularized by the Barnsley by defining the deterministic fractals, the natural way, the Fern, and all. So for example, we have the deterministic fractal that we are generating by the mathematical functions is one of the very important, and even we are just going through in our undergraduate or the postgraduate courses. That's the Cantor set, and similarly we have the subsequency gaskets. We have the different type of the exact self-similar figures in the mathematics, which we are defining by the mathematical equations that are called the deterministic fractal. So how we are mathematically defining the fractal as by the functions. So the construction is here. The overview I will give it in a very quick way. So the iterating, so we are using the iterating function system. What is that? We have a space X, and we have the set of finite set of the continuous functions. We call this space or this set as the iterating function system, while we have these functions as the contraction mappings on this X, that is the complete metric space. This is called the iterating function system. So like here in the Cantor set, we have the two functions. So if we have a real line with the usual Euclidean metric, then f1 and f2 is called the iterative function system. Here the f1 will be x with 3, and this one is another function. We are getting the deterministic fractal. So then what we are doing, so to construct the deterministic fractal or to verify whether the attractor exists there or not, so we are using one type of the hyper matrix that's called the Hausdorff matrix. So what is this? So we are taking a matrix space x comma d, and we are taking its family of the non-empty compact subsets. So we are denoting it in this way. So then the distance, we are defining the points at distance as the usual topological way. So the distance from a point X to the point B is the minimum distance from, if this is my point X and this is the set B. So we are defining the distances to the every point of this B and taking the least one distance from this, that's called the distance from a point X to the point to the set B. Then the distance between the two sets is defining as the maximum of all those distances is called the distance from A to B. For example, if this is my A and this is my B, so we first define the distance with respect to every, take the minimum one, and then define the distance from this one, take the minimum one of this one, and take the minimum, take the maximum of all these minimums. That's called the distance from the set to A to the set B. And what is the Hausdorff distance? So the, as we know, see, this distance is not defining a matrix. Okay, so this d of a comma b is not defining a matrix. So d of a comma b is not equal in general to d of b comma a. So it is not defining the matrix space. So then we are using the Hausdorff definition. So this is h of a comma b is d of a comma b, d of b comma, we are taking the maximum of this, that's this. Then this space h of x with this h is defining a matrix, and that's called the Hausdorff matrix space. Okay, so that's why this is called the Hausdorff-Pompeo matrix. Even this usually we are calling it as a Hausdorff, but I have read one of the paper, it's this emphasizes it, it should be the Hausdorff-Pompeo, because actually the concept has been given by the Pompeo. So he used the, instead of the maximum, he used d of b comma a, then the Hausdorff gave this maximum, and now we are calling it as a Hausdorff matrix. Okay, now, so then what we have these some of the results that usually we know that if we have the three sets, compact subsets of the space X, then if A is the subset of B, So if A is the subset of B, then the distance from A to B is equal to 0. Similarly, if you have the distance from A to C, it holds the triangular inequality. So d of A comma B plus d of B comma C. Okay, so this is the distance from A to B that we have already defined the distance. Okay, so now this is the main important, I write it again, important lemma that actually fails in most of the contractions when we are showing that whether this whether the map is is the same contraction in the Hausdorff space or not. So what it says, if we have the two finite collection of the sets, then this this inequality is true. Okay, so these are the basic things. Just I will go through it very quickly. So then what we are doing, then we are defining the then we are defining a map T, okay, or W, from this one to this one, and now this map, it has the elements as the sets, it has the elements and the sets. Then if this is again a contraction, then we say that there exists a fixed point. So that means W of A is equal to A. So this W of A is the union of Wn of A, and this is called the attractor. Even in general, we are calling it as a attractor. In particular, we are calling it as a fractal. Okay, clear? So now then, as I told, that it has been Hutchinson used to define this IFS on the to define the self similarities in the sets and iterating function system. He mentioned he used the Banach contraction. Then the Barnsley have used this IFS in defining the different natural objects. Okay, so he popularized it. Then the Hatta came and he used the phi comparison functions. He used the phi IFS instead of the Banach contraction. He used the phi contraction, and he said that every Banach contraction is inside this, and that means every Banach contraction is the phi contraction, but every phi contraction is not the Banach contraction. And he used it to show that this if you have the phi contraction in any matrix space, then it is also a phi contraction in the Hausdorff space as well. And he has shown the yeah, the attractor in that space, hyperspace. Then different mathematicians came. They used it to define the infinite IFS. As in the IFS, we are taking the finite number of the functions contractions, but they used the infinite number of the contractions, and they used it to find the infinite IFS, and used it to find the attractor. Similarly, the Sicilian came. He used the F contraction, and he took the countable number of the contractions, F contractions, and he used it. So he has done the work in the IFS as the countable IFS. Then the Chand and all from the sir from the IT Madras has used the cyclic contraction. So that has already done by the Viramani sir and the Crick. So cyclic contractions, he used the same and find the cyclic IFS even with the phi contraction and the Banach contraction as well. So then the Prithvi used the Hutchinson-Barnsley fractal. He classified it active and the dull on the interpolative operators, and they used it to define on the different contractions whether which fractal is active and which is dull. Okay, now the main question is, for example, we have the different types of the contractions. Almost, I think we have the more than the basic contractions. We have the 100 types of the contractions. Is it possible to define the fractal or the attractor on all the contractions? Just like this is a Banach contraction, this is the Kanan contraction, these are simply the points. Okay, so similarly we have the Reach contraction, we have the Chatterjee contraction. Is it possible to define the attractor or the fractal on every space? That means on every 100 contractions. So first of all, I want to just let you know here, we are calling this function as a conventional contraction, and this one we call as a non-conventional, because we have here the addition with the, for example, x and t of x, y and t of y, or x and d of y, like these. Okay, so these are the unconventional and Banach is the conventional. Now I want to show you one here. Here example, this one. So Sahu as and all, they have just defined the Cannon iterating function system simply, that has been done by the Banach. But the Petrosel came in 2020. He used the same thing and showed that their definition of the contraction, their definition of the IFS is wrong. Even they use it as the well-known contraction, even the Cannon contraction, very famous contraction. So the characterization, it gives a good characterization of the compactness of the space. But one thing is there, they could not make the Cannon contraction in the hyperspaces. Okay, they showed that it is not wrong, and they gave the example. Then even then we have done the work here. I showed that recently the paper came, d-symmetric space. Okay, this paper came recently. I showed what are actual the conditions why it fails to be, the IFS fails to be in the usual hyperbolic matrix, Hausdorff matrix space. Okay, so now then what we will do in this paper, we took a function that's called the weak phi function to define the attractor in the Hausdorff matrix space. First, we have here the wire from this game. So actual in 1969, so Boyd and Wong introduced the phi contraction that generalized the Banach fixed point, and then the elder and this, what is this? This is d of x comma y is less or equal to phi times d of x comma y. So this is called the weak phi contraction. This is called the phi contraction. This has been given by the Boyd. And then the elder came. So he used it to define the weak phi contraction. They used d of x comma y is less or equal to d of x comma y minus phi times d of x comma y. And this is called the weak phi contraction. Then the Kirik and all, they defined the cyclic contraction on the another way. Then this Russ unified the notion of the phi contraction and cyclic contraction. Then the Karpinar came. He used the cyclic property, he used the weak phi property, and he defined the cyclic weak phi contraction. And then we have worked on the cyclic weak phi IFS in the Hausdorff space and show that the attractor exists there. Now in this paper, so now we are defining the cyclic weak phi in the tupling mapping. Okay, tuple map. So what is that? We will define it. Okay, so the first thing is that we first establish a strong M fixed point in the usual matrix space, but the Cartesian product of the n closed subsets of X utilizing a function phi, that is weak phi. Then the second step is that we will use the same function on the Hausdorff space and show that by the iterating function system, the by the associated Hutchinson operator, the attractor exists there. Okay, what is the M tuple fixed point? Okay, so what is M tuple fixed point? So an element, this one, x1, x2, xm, is called the M tuple fixed point. Okay, if we have a function from xm to x, if it satisfies these conditions. Okay, so this one is from xm to x, f is a function. So if it satisfies these conditions, we call that this element, okay, is x1, x2, xm, is called the M tuple fixed point. Then look at here, yeah. So here the condition is that f of x1, x2, xm is equal to xm. Then this is called the fixed M, this x1, x2, xn, this ordinate is called the M tuple fixed point. Okay, now if f is a map from the M fold or the M Cartesian product of the spaces up to the x be a mapping, then M tuple fixed point of f exists if and only if you have defined a map f such that this map has a fixed point xm. Okay, so if this map has a fixed point, then this one map has the fixed point. Okay, so this is the definition defined by Soleimani. And then the even the Imad and the Karapinat have used to define the M tuple Banach contraction. What they did, they took the F map on the xm to x and they said that this is the M tuple Banach contraction if there exists the constant k such that this property holds. Because it is very simple, d of f of x comma f of y is less or equal to k times d of x comma y. Now what they did, f of x is now obviously from xm, it is defined on this and this will be defined. Now here they are taking this summation of d of xi comma yi. Okay, like this. So divide by m. So this is the M tuple Banach contraction and they have shown that it has a fixed point. Okay, now we have the class. As I told that the different mathematicians have used the phi class functions to define the phi contraction. So what is that? They said that if phi is a positive real valued function, so we say that this belongs to the phi class if it satisfies the condition. Phi should be upper semi-continuous and phi of t is phi of tau is less than tau and tau is greater than 0 and phi of 0 is 0 at the 0. Okay, now so here now what is the strong M tuple fixed point? We say if f is a function from xm to x, an element is called the strong fixed point if f of x, this means from the m ordered point, will be equal to x, because this is from up to the x. This is called the strong M tuple fixed point. The cyclic map, so f of a1 should be the subset of a2. Then if you will take the map of this one, it will contain it a3. Yes, and similarly the last one. Yes sir. F of am will again come to the a1. So this is called the cyclic mapping. Okay, so now what we will do, so we will take a function. Okay, now we are coming to the main result. First what we will do, we will show that the fixed point exists by the weak phi tupling contraction that I already know. In the usually we are writing d of x comma t of x, sorry, d of x comma t of y is less or equal to d of x comma y minus phi of d of x comma y. Now we are using the, since this t, now here we have the f, so it is from xm to x, this one, so we will apply the previous results. So why when we call this as a weak phi tupling, so we say that first it should be the cyclic, so for the cyclic weak phi contraction. Second is that there should exist is one the upper semi-continuous function such that this property hold. So this f of x and f of y means x1 x2 so on up to xm and y1 y2 so on up to ym, and on the RHS this one hold. As I told, we have d of on the RHS greater or equal d of x comma y minus phi of d of x comma y. Now as you have seen in the as you have seen in the Banach contraction, what we are taking, they have took this one summation, so we are using the same result here to take the summation on each of the d of x comma y, and we will show that it has a fixed point. So that this is the main result, that is if we have the closure subsets of a complete matrix space x comma d, we will define a map. Then this is called, if this is a cyclic phi contraction, so with respect to this a1 a2 so an, then it has a fixed point. So first condition, it has a fixed point if the intersection is MPT. So second thing is that the fixed point should be unique. Okay, so the structure of the proof is that first we define the sequence of the by the cyclic property of f, we will show that it should be the intersection will be non-empty. Then we will prove the distance limit, then we show the sequence, that means sequences are Cauchy via contradiction, and show that the triangular contraction inequality means, under this complete matrix space it will converge. Okay, so then convergence will be there, and then we verify if the fixed point is there, that will be unique. Okay, so this the goal is the first thing that I already told, that we will show that it is non-empty. So we are first taking the initial conditions. So x10 belongs to a1, so we have to take the intersection is non-empty. So we are taking the point from the a1 because we have the closure subsets. So this is the initial condition. So then define a sequence using the cyclic natural. What is this x1? So that will be the obviously the map of the previous one, so by the condition of the f. So similarly the x2 will be this one, x2 and xm. So since it is cyclic, so by the cyclic property, so one will be contained in another will be contained in another. So the intersection, so xi belongs to ai for all ai and all n. So that means this will be intersection will be non-empty. Okay, so now I want to let you know here. So here we see we have the superscript and the subscript. So this is superscript, subscript. We are calling this as a vertical distance and the horizontal distance. So to usually in the fixed point theory, what we are showing, we are taking xm and xm plus 1. First we are showing the convergence, then less or equal to epsilon. Okay, then we are showing the every Cauchy sequence is convergent. Okay, we are taking the Cauchy sequence, then we are showing that it is convergent by the completeness property. So now here we have the goal is here we have to move along with the vertically along with the horizontally. So we will take the sequence in this way. Okay, we will take the sequence in this way. One is horizontally and one is vertically. So we have to show it is equal to limit n goes to infinity, it is equal to 0. So then for a fixed I, we will apply the phi contraction and show that it has a fixed point. So now take this sequence d of this distance of the sequences xi and xi plus 1. So apply this xi will be by the definition of the f, this will be in its preceding one, so that will be xi minus 1 and so on. For this xi plus 1 it will be in its preceding one, so that will xi. So then use the, since d is a, we already said that this is a weak phi, so we use the weak phi contraction, and let we take the sum over n, and then this one, let we have this one as a sequence an, and then an by the summing the inequality here, so we will have an plus 1 is less or equal to an minus m times phi of an divided by m. So now, so an is greater or equal to 0, sum of the distances. This is monotonically decreasing, so an will converge, let's say it will converge to the r. Okay, and that will be obviously greater or equal to 0. So then let's say this is converging to r by the previous property, r less or equal to this r minus m of r minus 1. So r is less or equal to r minus m of phi of r minus 1. So that means this one should be equal to 0. This second term will be 0. If this is equal to 0 by the phi property, then the internal element should be equal to 0. So that means r by m is phi of r minus r by m is equal to 0. So that means r should be equal to 0 by the phi property. Okay, so that means this an is converging to the 0. Similarly, we are taking now the sum over the b, that means second term. So now we are taking the vertically I and I plus 1. So taking the n as a same, and you will again see by the same contraction property, again the same property we are using, and we will show that it again converging to the 0. So by using the triangular inequality, so in the triangular inequality we will show that it is by the triangular inequality, so it is less or equal to this one and vertical one and the horizontal one. So here you will we will keep this as a constant, here we are changing it. So then this is already going to 0, this is already going to 0, so this is equal to 0. So this is the first thing. Then the second thing that we have to prove the sequence is a Cauchy sequence. So by the contradiction we will say that at least one sequence is not Cauchy, and we are taking the two sequences here. So, let's say epsilon is greater than 0, and taking the subsequences such that this one is greater or equal to epsilon. Okay, so but with the indices here we are choosing so that the summation will be this are equal to epsilon by the previous result. So we will define the two terms here and showing it that this limit is going to 0 from the previous step. Okay, so taking the triangular inequality, and we will show that no, our supposition is wrong. Okay, this is the usual proof. Okay, so when this is we are showing that the limit is going to 0, so our this result is contradicting. So then we show that every sequence is Cauchy sequence. So this is the complete, so it will converge to a point. So since ai those subsets are the closed subsets, so that means xi, these sequences will converge within the subsets only. So that means the distance this from this step we proved that the distance is 0. So that means taking the limits, so we will show that x1 is equal to x2 going to the same converging point as the epsilon, and that will be in the intersection of a. Okay, so then we will show that this is a fixed point, that converging point is a fixed point. So we will use the triangular inequality. So by the triangular inequality, okay, so by the triangular inequality here, what we have, so we will use the definition of phi and show that this is equal to the same epsilon, it will converge to the same. So that's the fixed point. So this is actual the structure of the proof that we are usually following in the topology. But here one thing is that we have to go through the two distances. One is the vertical distance and another one is the horizontal distance. That is only the difference in the proof, otherwise the same thing is there. But here one more thing is that it has the phi contraction due to the negative sign. It is becoming little sometimes difficult, but the proof is very simple. Okay, then showing the uniqueness of the fixed point as usual. Okay, so we are showing that this is unique, and that means we are getting a fixed point. Okay, okay, so then we have some examples. Let's say x is union of ai we are taking this way, and taking that t of x is equal to minus x by 3, phi of t is a 2 t by 2, and taking the distances, you will say it will converge to the 0. Similarly, in this way you will define, this is already, this example has been taken in the paper by the Tanmoy. Okay, Tanmoy, so who defined the phi contraction or the tupling, phi tupling contraction, and they used this definition and showed the it has a fixed point 0. Even we have showed that it has a fixed point in the weak phi contraction as well. Okay, now as see now the different as I told you that the different contractions in the different directions has been came, just like some have used the different function. Okay, so functions has been changed, or the generalized functions came, just like the phi function, or some has changed the metric only. Okay, some have changed the metric and use it to define the different contraction in the different metric. Some have used the different functions. Okay, so they use it to generalize it. So is again I said that is if the contraction comes, then the fixed point comes, is the same possible in the Hausdorff space where we have the function from the h of x to the h of x. So I have already shown you the example. Not every function or not every contraction is able to do so. It's not possible for every contraction to define a attractor in the Hausdorff space as well. So let's check whether weak phi is able to find the contraction, whether it is able to find the contraction, whether it is holds as a contraction property first in the Hausdorff space or not, and second we will then check that whether it has the attractor or not. Okay, so we will do it here now. So weak phi IFS. So in the weak phi IFS, obviously it is a definition of IFS. So in the IFS, we have a set and complete space x comma d, and we have the closure subsets for the cyclic generation. Okay, for the cyclic weak phi IFS. So we have this closed subsets of this x. Then we have the finite maps, which are the weak phi contractions. That's called the weak phi IFS, and it is hyperbolic. Okay, now we have to check whether this IFS generates the attractor or not. Okay, so we will define a by the Hutchinson operator, we will define this f tilde and we will show that whether it has a fixed point or not. That will be a set. Okay. Okay. So what is that? So here we have, so x comma d be a complete matrix space. F is a function from xm to x that will be a continuous weak by tupling. Okay, so one thing is, here we are taking here continuous. In the previous we did not took the continuous, so here we mentioned the continuity because weak phi contraction may or may not be continuous. This is also a one good thing in the generalization of the contractions, because every Banach contraction is continuous, but there are the different contractions as well which are not continuous but having the fixed point. So here weak phi may not be continuous, but to preserve the compactness, image of the compact set is compact, so we are using the continuity property here. Okay, so this is also a question, that can we relax the continuity, uh, can we relax the continuity in the in generating the attractor, okay, by this contraction. Okay, so then we define the another map from the that means Hutchinson, Hausdorff h of x means set of the non-empty compact subsets. Now we are taking the m tuple here up to the h of x, so we are defining the f tilde. Will show that in this is, if this f is the weak phi contraction, is the f tilde also the weak phi contraction? If it has the weak phi contraction, then it will have the fixed point, so we will show that one as well. So what is our motto here? So first, so if we the first thing is, we will take the two subsets of compact subsets belongs in the h of x, so we need to show that this one is true. Okay, so this one is true. So now this f of b1, you know, f tilde of b1 will be b1 comma b2 comma bm. Okay, so I wrote in short here. So f of f tilde, so this one will be the bm. Okay, so similarly b2, b3, so b1. Okay, so this even it will belong in the t of a3. Okay, because the image will go to the by the first order first element of this ordered tuple. Okay, so using the definition of the Hausdorff, we will show that it has a complete, it is a contraction, then it has a fixed point. Okay, so okay, now what first I want to just write the overview of the proof, what we have done. We have proved this theorem. Okay, so we have proved this theorem. I want to write it here, what we did actually. So first of all, since the T is the uh, cyclic map, so for all bi, sorry, okay, for all for all bi that are in the T of ai, okay, because this will be in for any set, it will be the image of any of the element. Okay, so T is continuous, so that means f tilde of b1, b2, so on up to bm, this will be contained in T of a2. Similarly, f tilde of b2, b1, it will be in the a3, T of a3. Okay, so because this is a cyclic, so let's say we have the element b1, b2, and we have the element bm1. So this is the element, and we will take the another element, obviously b2, b3, b1. So it will be, these are the two elements of h of x m. So now see, we have here the horizontal distance. See, the superscript is same, so we are using the maps. Maps is changing the subscript. So now we will take the arbitrary element x1, x2, xm. So obviously this one will be from this one b1. Okay, then the distance from f of x1, x2, xm, keeping the superscript same, with f of x, let's say f of b2 from up to this set, b2, b3, b1 m. So this is actual the distance from a point to a set, that will be minimum of the distance from the points and the points up to here, and we are showing at the end. So I will directly write the result. We have shown that the distance, this distance, that is distance from f of x1, x2, xm from one set, this up to the set b2, b3, b1. Okay, so this will be less or equal to d of x1, x2 plus d of x2, x3. The superscript is same, d of xm, x1 square divided by m plus phi term as well. If this is, let's say this is star, so this is phi of star. So we have proved this one. Then since this phi is decreasing, as we did in the fixed point theorem, as the phi is decreasing, what we are showing, so we are showing that this one will be, that means d of x1, x2, xm, x2, x1, superscript is different. Here we are taking from the set 1. So these two will be d of b1, b2, bm of the first set, b2, b3, b1 of the second set is less or equal to the distance of h of this one, because d of a comma b is less or equal to h. So we have proved this one. Then taking the, since phi is decreasing, so we are saying 1 by k1 phi of something will be less or equal to phi of d of that one. Okay, so then we are showing that this is again a contraction. See this one. Okay, so it is well defined, and then we show that this is the contraction in the hyperspace. When this is a contraction in the hyperspace, then it has the fixed point, and defining the cyclic v phi ifs with the Hutchinson operator, we are proving that it has a fixed point. That fixed point is called the fractal attractor. Okay, so like here we are taking the sets in this way and defining the function in this way and showing that it has the attractor. Okay, so these are the some references of this paper, so where from we got the things there, and up to this we have done the results up to the in the tupling fixed point. So this is the means we can define the attractor in the m folded maps or the m folded contraction mappings. Thank you very much. If anyone have a question or any suggestions, since we are still doing some improvement in this paper, so if anyone have any suggestion or any question, you may ask. Thank you.
Thank you, Kifayat. That was a wonderful talk. I'm now ending the recording.